Howdy! Our presentation today is on a cost-effective entangling prefetcher for instructions, and my name is Jay Bagali.
My name is Stephen Claypool.
My name is Zihao Pen.
And my name is Purni Sinowasane.
And together, we are from the Texas A&M University GigaMags. This page provides an overview for the rest of the presentation. We will start with introducing the concept of the entangling prefetcher and highlight key points of why we should care, what applications does this extend to, downsides of not having a prefetcher, and obviously the major benefits of having one. Then we will give some context and background on some other major prefetchers within the field, such as the NextLine and RDIP prefetchers, and then we will explain our implementation and how we perform the simulations to get our results, which we will then discuss and summarize our results and findings as well as other key parameters discussed in this presentation within our conclusion. All right, so conceptually, what is a prefetcher and how does it work? Well, the main idea behind one is to fetch the data before it is actually needed by the program. A prefetcher can be a hardware or software component designed to anticipate future memory accesses and retrieve data or instructions from main memory or secondary cache before they are explicitly requested by the processor. The main idea behind prefetching is to reduce the latency of memory accesses by bringing in data closer to the processor before it is actually needed, thereby improving the overall system performance. They monitor access patterns and speculatively fetch data or instructions that are likely to be accessed soon based off of these observed patterns. But exactly why should we care? Well, because memory latency is high, and prefetching accurately and early enough can hide this latency. Additionally, compulsory misses can be eliminated. There isn't a need for state recovery, unlike branch prediction, and there is a need for lower access latencies, especially in our age of modern processors. Nowadays, large cloud and server application instructions are getting further away from fitting inside the L1 instruction cache. They can suffer from high miss rates and incur more stalls. And applications such as in-memory databases, graph tree processing, in-memory data analytics, as well as data center workloads cannot make up for this increased latency. And as you can see over here, instruction fetch stalls can block the pipeline and ultimately lead to performance degradation. So what exactly is our solution? Our solution is to leverage timeliness, which is the ability to bring instructions into the cache at just the right moment before they are actually needed for execution. More specifically, our solution is called the entangling prefetcher for instructions, which entangles instructions to maximize this timeliness. Now, two major challenges that the entangling prefetcher encounters is that bringing instructions too early means that there is a higher risk of being evicted before it is used. And the other challenge is that bringing instructions too late can lead to instructions arriving after they demanded. So the entangling prefetcher works by finding out which instruction should trigger the prefetch for a subsequent instruction.
Let's look at why the first attempts at speeding up computers with prefetching weren't perfect. Initially, systems like the next line prefetcher just grabbed the next set of instructions in line, which worked fine when things were straightforward and predictable. But as programs got more complex, these simple systems started to struggle because they couldn't always guess correctly which instructions could be needed next. RDIP, which is Written Address Stacked in Directed Instruction Prefetcher, enhanced this by using written address stack to predict instructions post function calls, which increased the accuracy. Another prefetcher, which is Distant Joy Prefetcher, which was built on RDIP's foundation, introduced a dual look ahead mechanism and context based signatures for more precise prefetching. Although it was more accurate than RDIP, it requires higher computational resources and can still mispredict in complex applications. Although effective to some extent, these models often suffer from higher miss rates and increased latency when dealing with large scale applications, such as in memory databases or data center workloads. For instance, RDIP relies on written address stacks, which limits its applicability and accuracy in dynamic execution environments. Recent advancements in prefetching are making computers smarter about handling instructions. Let's break down a few of the latest technologies. Wrong path aware entangling prefetcher. Think of this as a smart assistant that helps correct mistakes before they happen. It spots when the computer is heading down the wrong path in processing instructions and quickly gets it back on track, which saves both time and resources. Protein. This is a resource efficient instruction prefetcher. This method is all about being adaptable. It constantly tweaks how it prefetches instruction by closely watching how data moves to the computer, which aims at using the resources more wisely and misses very few steps. PDIP, which is a priority directed instruction prefetching. This focuses on the most important task to keep everything running smoothly. By picking out critical instructions that impact performance the most, it tries to speed things up. However, figuring out which instructions are most important can be tricky, and sometimes the system might not be the perfect choice. Even with these cool technologies, it's a challenge to perfectly predict what instruction a computer will need next, especially as computers and programs become more complex. Our project is working on making this prediction even better, aiming for a solution that's both smart and cost effective.
First, I'll explain the concept of entangled accesses. After a sequence of accesses, assume there is an instruction L requested by the core that results in a cache miss. This miss results in a latency as the cache line is filled. With the computed latency, we move backwards in time to determine when a prefetch should have occurred for the access to hit. To determine exactly when to prefetch, we look at the history of accesses and entangle the prefetch to an access before instruction L. Access B lines up with the latency of access L's miss, but to simplify the process, prefetches are entangled to basic blocks, resulting in the entangling of access L's prefetch with the basic block starting with access A. Then, whenever instruction A is accessed, instruction L is then prefetched. Now I will explain the implementation of the entangling prefetcher. In the center is an 8-way L1I instruction cache. To the right, two registers are used to track the head and size of every basic block. Every new cache line increments the size, and once the end of the block is reached, the head and size are stored in the entangled table. When there is a cache miss, it is recorded in the MSHR with a tag and timestamp. When the cache line is filled, the latency is computed as the difference between the time of the miss and the time the cache line was filled. The history buffer is then referenced to determine which access source should be entangled given the computed latency. Once the source is determined, the destination is linked to the source in the entangled table. If a basic block head is accessed, the prefetches are stored in the prefetch queue, which then checks the L1I cache for a hit and moves to the next cache level if it misses. The prefetch queue also stores a tag and timestamp, which can be used to correct late prefetches by feeding the timestamp to the MSHR in case of a miss in the L1I cache.
In this slide, there will be a more detail about the process of managing prefetch misses and cache operations, such as access, fill, and eviction, within an advanced caching mechanism known as the entangled prefetcher. The entangled prefetcher is able to comprising entries that hold a source entangled cache line, also its associated block size, and a compressed list of destination entangled lines. So to further refine this, we incorporate a confidence counter for each destination to navigate latency variations effectively. The core components, including the level 1 instruction cache, the prefetch queue, the miss status holding register, which is the MSHR, are enhanced to record timing details and source entanglement data. Timing information captures the precise moment a request is initiated, while The source entanglement refers to the source line's location in the entangle table and includes an access bit that signifies whether the operation is a demand access or a prefetch. Entanglements are initiated upon detecting misses and late prefetches. This is done by searching for a corresponding source in the history buffer as depicted in the first and fourth columns of this chart. An entangle pair is entered into the entangle table. Upon their introduction, these pairs are assigned the highest confidence value as they are anticipated to be timely. However, adjustments to the confidence counter are made based on the nature of the prefetches. As shown in the first column, a late prefetch results in a decrement of the confidence counter. And then on the other hand, the counter is incremented following a timely prefetch as shown in the second column. And then the counter is decremented in response to a wrong prefetch, which is presented in the third column. This confidence mechanism plays an important role in the system's adaptability, increasing or decreasing the confidence based on prefetch outcomes. A timely prefetch enhances confidence, whereas late or wrong prefetches undermine it. When the confidence counter hits zero, the entangled pair is deemed invalid and subject to replacement, prioritizing pairs with higher confidence for retention. So this would have a balance between proactive data fetching and system resources, ensuring that the prefetcher responds dynamically to the different latencies that may arise from different levels of cache or system contention. So in this slide, we will talk about optimization. In optimizing our entangle prefetcher, we employ two layers of compression to maximize efficiency and minimize storage overhead. So firstly, there will be advantage of spatial and temporal locality in the basic blocks. And by identifying basic blocks that are temporally consecutive and spatially adjacent or overlapping, we can merge them into a single entry. This consolidation significantly reduces the number of basic blocks entries in the entangle table without compromising on prefetching accuracy. So the second compression strategy leverage the commonality in memory address bits. So since source and destination memory address frequently share the most significant bits, we can compress the representation of these addresses. Our structure uses 64 bits for each entries, 3 bits for dedicated to the mode of compression, indicating the number of destinations, which can range from 1 through 6 based on the mode number 1 through 6. So following each destination, we allocate 2 bits for the confidence counter. This dual layer approach to compression allows to pack more information into the entangled table. So it enables the prefetcher to efficiently handle multiple destinations and their associated confidence without requiring an extensive amount of memory space. And now we come to the methodology for the simulations. So in the simulations, we use a simulator called Chempson. We use the FDIP master branch as its version. And in this Chempson, we run simulations for 8 different L1I prefetcher. And then for these 8, we have the same configuration except the L1I prefetcher is different. And so first, the branch that we use is by model. And then next is the L1 IP fetcher. We have 8 of them. The first one is next line. The second one is entangling 2K entries, and then entangling 4K entries, entangling 8K entries, and entangling 16K entries. And also we have mini DJOT, DJOT, and also RDIP. For the entangling, we made it our own, and so therefore that is what we proposed. And here there's 4 different versions. We will see a different results for different versions of entangling. And then for L1, the prefetcher we use no prefetcher. L2C prefetcher we use no prefetcher. LLC prefetcher we use no prefetcher. And then for LLC replacement we use LRU policy. And then for number of core we use 1. And for warm-up instructions, we use 50 million instructions. And for evaluation instructions, we also use 50 million instructions. And we also have various traces that will be discussed in the next slide. And next, we come to the various chases for the methodology. So we use 50 chases from the first instruction prefetching championship as a competition focused on enhancing instruction prefetching algorithms. And the 50 chases that we use is separated into two categories. One is client, second is server, there is spec, and then this spec also has different categories. And so for the client has 8 chases. It's about the desktop applications for the end users. And there will be server. Server has 35 chases. Server will be about the high demand environment. And then for the spec categories, there is 4 different categories for the spec. One is GCC. GCC has 3 chases. And then GOP MK is 2 chases, and then Pro Bench has 1 chase, and then X264 has 1 chase. And by using these 50 chases, we are able to generate the results by simulations and output the speedlab and IPCs in the next slides.
This graph shows the speedup of every prefetcher we tested with respect to no prefetcher versus the size of the prefetchers. The entangling prefetchers all showed significant speedups while minimizing the size. The entangling prefetcher with a 16,000 entry entangled table showed diminishing returns given its size, showing that 4,000 to 8,000 entries in the entangled table is ideal for a high performance to size ratio. Some prefetchers, like djolt and mini djolt, showed similar speedup but at a much larger prefetcher size. rdip had worse performance with its lower speedup and larger size. Although the speedup of the next line prefetcher is low, the small size is great for reducing the code footprint of the prefetcher. This graph shows the IPC speedup of each workload in increasing order on all prefetchers. The 4K entangling prefetcher showed comparable performance compared to other entangling and state-of-the-art prefetchers, but the smaller size, as shown previously, makes it an ideal prefetcher for many workloads. Larger entangling prefetchers perform better than top-performing prefetchers like djolt, while still being smaller as shown before. Additionally, the entangling prefetchers never result in performance degradation with respect to no prefetcher like the next line and mini djolt prefetchers do.
Let's explore the key takeaways of our project. Our project shows that the best setup for our prefetching technology uses between 4,000 and 8,000 entries in its system, which helps computers process information quickly without taking up too much space. When we tried using 16,000 entries, it didn't really improve things much, suggesting that bigger isn't always better. Compared to similar technologies like distant jolt and mini distant jolt, our smaller system works just as well, if not better, and is more consistent across different types of computer tasks. This means our approach is effective at speeding up computers while still being efficient with space and resources, paving the path for even smarter technology in the future. To conclude our discussion, let's summarize the breakthroughs we have made with our innovative entangling prefetcher technology. Our team developed a prefetching system that not only speeds up computers but does so in a way that's efficient and practical. We found that our system works best when configured with between 4,000 and 8,000 entries. This strikes the perfect balance between quick processing and resource management. Our prefetcher outperforms traditional models, offering faster performance and better consistency across different computing environments. This means our technology can significantly enhance everything from corporate data centers to complex scientific simulations. Moving forward, we are excited to refine this technology further. Our goal is to make our prefetchers even more adaptive. This will lead to more efficient computing, reducing delays, and increasing throughput across all applications. Thank you for joining us today. I look forward to exploring how we can continue to push the boundaries of prefetching technology together.